All right, relays and contactors. This is from your module 030204B. Hopefully you've read through a part of this. It's quite the large ILM to read through, and there's tons of information in this one. So I encourage you to read through it as much as you can and try to follow along with the PowerPoint as we go through it today. Okay, so what we're going to do today is we're going to describe the different types of relays and contactors. We're going to interpret the nameplate information on them, which you kind of did in first year. Identify the main three parts of the relay, which again will just be a recap from first year. Describe the purpose of laminations and shading coils. We're going to identify application advantages and disadvantages of different materials that you use in the construction of the contacts for either a relay or a contactor. Identify advantages and disadvantages of contact configurations, so how they're laid out. We're going to describe the operation of relays and contactors, and connect and analyze relays and contactor operation. So again, it's quite the full PowerPoint, so I will go through it. If you need to pause it as we're going through it, I will not be offended. I promise. It's a lot of information, and I will try to get through it as swiftly as possible, but without leaving out anything important. So bear with me. Okay, so this picture I'm sure you'll recognize from first year. It's one of your left-hand rules from the three, but it's talking about an electromagnet and how we get the magnetic field for a magnet, and the purpose of that. And the purpose for it is to move an armature or a solenoid, most likely an armature for a relay and for a contactor. So electromagnet, again, it's a very simple thing. It's a piece of wire that's wrapped around a core. It can be an air core, but most likely going to be a soft iron core, and it's a higher permeability, so it's going to allow that magnetic field to strengthen. Okay, so electromagnet definition here is a voltage applied to a coil, causing current to flow through the coil. This creates an electromagnetic field, and the core becomes a magnet, and that magnet is what is going to be moving your armature. Right? Okay, so here is your cross-reference of cross-sectional area of relay. Right, so we got the relay coil and the core. Again, in a relay, your core is not movable, it's stationary. We have your relay coil connections. Okay, so all of this right here, that would be your control circuit. So you could have a push button or a single pole switch or whatever controlling the current going or not going to the relay coil, and that would all be the control circuit, so a lower voltage for that setup. And then for your power circuit, you have your contacts. You can have the common, right, which is down here attached to the armature. Then you have your normally open contacts and your normally closed contacts, and those two terminals right there. We have your armature, which is electrically isolated from the magnet here and from the control circuit. We have a return spring, so when this field collapses, the armature will return back to its original state, which is going to return the contacts back to the original state. And of course, the common terminal connection, which we're always going to bring our power to. Right? All right. So as you can see here, there's one coil, right? And this one coil is going to be controlling 3 normally open contacts and 3 normally closed contacts, which means this relay here has 3 electrically isolated armatures attached to it. They're all going to move at the same time, but they're isolated from each other, and each one of those armatures is going to have a normally open and normally closed contact hooked up to it, just like we have here. All right, the 4 types of relays we're going to talk about today. We have plug-in relays, so the general purpose. They're smaller ones, sometimes transparent. They call them ice cube ones, or ice cube relays, usually for up to around a half the horsepower. Okay. Then we have industrial control relays. Obviously, it's going to be larger for heavy-duty setups than industrial control circuits. Then we have power relays. Relays used for direct switching of small motors and heating loads. These power relays are not used often for switching, so they're not like a general use switch. So you're not going to be turning them on and off lots, right? They're not meant for that. And then ELV lighting relays, we talked about that in first year, usually from a solenoid where the actual plunger is going to move, the core is moving, not the armature. But it's a type of relay used to switch commercial lighting systems. Okay. So here is your plug-in type. You might recognize this from first year. Okay. They usually have, as you can see here, it's like an ice cube with a bunch of spades in it, and those spades or pins plug into a base, right? And they can only plug in one direction, so those pins are going to go to the proper terminals, right? And these terminals are going to be labeled on. They could be on the bottom or on a legend telling you what terminal is for what purpose, like the comma terminals are normally open, normally closed, etc. So these ones are great for if they burn out, something's wrong. You literally just have to unplug it, just pop it out. You don't have to unscrew any wires or do anything and just pop a brand new one in. So they're very handy like that. But again, they're not going to be used for anything much more than half a horsepower motor loads, right? Usually up to around 15 amps max. Then we got industrial control relays here, which look much heavy dutier, right? Because they are. These ones say normally used double make, double break to reduce arcing. We're going to talk about that in a bit here. But these ones here, it's the same setup. It's a coil, there's armatures, there's contacts and everything. It's just heavy duty. It can handle more current, right? But these ones are interesting because you can add controlling decks, or they say adder decks, right? These decks you can put on top to add more contacts for timing or different controls. So these ones are general use, but you can adapt them to make them used for a wider range of purposes. Okay. We got our power relays. You may recognize one of these from first year. It was on your relays board. All right. These are rated for up to around 30 amps and say 2 horsepower motor loads. It says low cycle rating of switch. It means you are not going to be using this guy and switching it on and off and on and off and on and off. Okay, they're not meant for that. Yeah, so they're, again, general duty, a little heavier duty than those ice cube ones. They can handle up to 30 amps. Right. One problem with these guys are they are fully exposed. Right. So you have that. There's your armature right here, and your contacts. If you have 30 amps traveling through, this is all exposed, which means if you touch that, you got 30 amps going through you now potentially. So not on the safer side, but they still work. Right. Then we got our low voltage lighting. Again, the solenoid type with your plunger, right, which is the core of that coil, is actually moving and opening and closing contacts. And they're going to be latching relays. So it's going to mechanically latch in place, either on or off, or open or closed. You can see here, you can manually turn it on or off. If something happens, if it gets jammed or burnt out or something, you can actually manually, with the screwdriver or whatever, to turn on the lighting or turn off the lighting. It's going to force the contacts open or closed. Okay, but this is everything from first year, nothing new at all. You're just bringing that over to second year. So it says coils operate at less than 30 volts, right? So they're not rated for anything more than 30 volts. And it's just a bump of current. You're pushing on button. It's going to give a bump of current to the on coil, which is going to move the solenoid and close your contacts. And then you're going to do a bump of current to the off coil from the off push button. And it's going to move your solenoid again, which is going to open the contacts, turning off your loads. All right, then we have contactors. So relays and contactors are, in general, the same thing, but contactors are for switching much higher currents, right? When you get much higher currents, you have a problem with arcing, which is going to damage your contacts. And then having materials large enough to handle the higher amount of currents. So that's why contactors are just physically bigger relays. So here we have a contactor, okay, side view of a contactor. We have our coil, which is right here, our core and coil. We have a switch, which is going to be controlling that coil. All right. This blue thing right here looks like a little anchor. That's our armature, right? Hooked up to this armature right here, right? And that has these springs, right, that are going up to contacts here. And these are called bridge contacts because there's 2 of them for each set, right? Okay. So when the switch is closed here, right, just like in this picture here, the armature is going to move up, right? And these contacts are going to come in contact with each other, closing. Right, as we can see here, we have a coil, and these normally open contacts are going to close. We got line 1, line 2, and line 3. And then T1, terminal 1, terminal 2, terminal 3 are what's going to be going to your loads. Okay. So, yeah, we'll talk about the pins here and the springs afterwards, and a couple of other pictures. But a contactor is just a larger relay used for switching higher currents. Okay, so here's a cross-sectional view again. We have a 24-volt source, push button, hooked up to our coils here. We have 2 coils, right, hooked up in series. So when I hit that push button, we have 24 volts traveling through in series for both these coils, so 12 volts each, right? And a magnetic field is going to be created in this core right here. So this M-looking thing, sideways M or E, whatever you want to call it, is your core. And it's going to create an electromagnetic field here, which this core is now becoming a magnet, right? Then we have return springs here, right? And what's going to happen is this armature, or this, yeah, I guess you could call it armature, is going to pull down and be attracted to this magnet here, right? And when you do that, these springs here are going to compress, right? So it's the magnet here is overcoming the strength of these springs, and it's going to pull it shut, just like so, right? And compress these springs, and also these contacts are going to close, right? And compress those springs a little bit too, all right? And then, once those contacts are closed, I now have a path from my other source over here going through my contacts to my light, so my light turns on. Okay, so the purpose of these springs here and these springs here are 2 different purposes. These ones here, when I have a lot of current flowing in a circuit and I try to break that circuit, what happens is I have arcing, right? And I want to try to limit the amount of arcing I have on a circuit. And that's why they have maybe 2 sets of contacts or bridge contacts. In this case here, they want to try to, when the current is cut from this coil, right? So this push button is opened again. The current is cut from here, so the magnetic field is going to drop. These springs are going to try to, as quickly as possible, open up, right, this bridge here, but really what they're doing is opening up these contacts here, which has the high current going through it. Okay, so these springs are trying to push away as quick as they can to open up these contacts here, and the sooner you get those contacts away from each other, the less arcing is actually going to happen. If those contacts open up slowly, you're going to get lots of arcing, you're going to get lots of carbon, you can get pitting in the metal and damage done to your contacts, which is not good because it's going to cause resistance and hot spots. So these springs here are to open up your contacts at a speedy rate, okay, after they've been closed. And these ones here are to, when you close the contacts, right, sometimes if these were solid, if these springs weren't here, these springs right here, if they weren't there, and these contacts closed very rapidly, they can actually hit so hard they bounce, okay? And if they bounce, then you're going to get arcing. And if you get arcing, you get heat and carbon buildup and all those problems, right? So the purpose of these springs here is to, when it hits, the springs can absorb that pressure, I guess you call it, that contact pressure, and they're going to compress a little bit, but the contacts aren't going to bounce. They're going to stay together until that force is limited, and those contacts are then just closed, period. So these are going to reduce the amount of bouncing, or I guess called bouncing, when those contacts are coming into contact with each other at a very quick rate. Okay, hopefully that makes a little bit of sense. Talking about contactors, there's something called pull-in and or seal-in and drop-out voltages. So your seal-in voltage is how much voltage do I need to have to actually move my armature and seal in and get my contacts to actually close, right? So when I apply, say this side here is 24 volts, right? How much current do I have to have? How much voltage do I have to actually get this guy to move? Well, I'm saying here, the armature pulls in at approximately 85% of the rated voltage, and that's my seal-in voltage. So at about 85% of the voltage that is going up based on the sine wave, at about 85%, it's going to move in, the armature is going to pull in and seal in, and which are going to move those contacts and close the contacts or open them based on your circuit. Okay, so 85% is something you're going to have to memorize. That's your seal-in voltage. And then for armature to release, right, so as your voltage starts to go down, right, your voltage is getting lower and lower and lower. At about 50% of the voltage for that armature, it's going to drop out. So that magnetic field is not strong enough to overcome the springs anymore, which means these are going to open at about 50% of the voltage rating. Okay? So, if my voltage, say my coil is rated for 120 volts. Let's go back to this guy here. Say these guys are 120 volt rated coils. Right? So just disregard the 24 volts. Right? It's a 120 volt source here, okay, for my coils. The voltage to actually get this armature to pull in is not going to be 120 volts. It's going to be 85% of 120 volts. So it's going to be 102 volts. Right? You can just take 120 volts, multiply it by 0.85, and it's going to give you 102 volts. Okay, so that armature is now sealed in 102 volts. It goes up to 120 volts. Great, it's still sealed in. Everyone's happy. All right, for the armature to release, okay, that sine wave, when it's dropping down, when it gets to about 50% of that 120 volts, that armature is no longer, or that magnetic field is no longer strong enough to keep the armature pulled in and overcome those springs. So we call it the dropout voltage. So it's going to release, right? So 50% of 120 volts is 60 volts. So to get my seal on would be 120, and your dropout would be 60 volts. These two numbers here, 85 and 50%, you're going to have to memorize for sure. So write them down, do cue cards, whatever you need to do. Super easy questions for exams and quizzes. What is my seal-in voltage, and what is my dropout voltage for a circuit? And they're talking about here for the coil, right? The coil of the armature, or sorry, the coil of the relay or the coil of the contactor. Okay, so that's all. I promise you it's all going to come into play of why I've already been talking about that. All right, contactor operation. Okay, so you might recognize maybe this formula from theory this year if they've talked about it, but maybe from first year they might have talked about it a little bit. But we're talking about inductance, right, in henries. So inductance is, we have three things. We have induction, which is if I have a magnetic field and I bring a piece of wire through that magnetic field, I'm going to induce a voltage into that wire. Inductance is when I have, let's just say, a current going through the conductor, but inductance is my conductor magnetic field is cutting through another conductor magnetic field in that coil. So it's going to be producing a voltage, or sorry, a current traveling in the opposite direction of your main current, right? And in theory, they'll draw it on the board for you and make it a lot easier to understand, I promise. Okay? Then you have inductance and reactance, and that's your effect based on that current opposing your main current, and it's going to slow your current down. So when you get into phasor diagrams, you're going to see the effect of coils. It's going to slow your current down. Your voltage is going to get to its peak before the current does. Okay? All right. So we have inductance. And the formula for inductance equals N squared, so the number of turns. Okay, so that's talking about the coil, how many turns in the coil I have. Okay, I'm going to square that number. Okay, this funny looking U here, that's permeability. Right, so that's based on your core, how permeable that material is based on air going to or an iron core. And then the area of your core, right? So the cross-sectional area. And then down here is the length of your flux path. So that's how far your flux has to travel to get from north to south, pretty much, okay? So just like Ohm's law from first year, my inductance, if I increase the number of turns, if I increase the permeability, or if I increase the area of the core, that will increase the inductance. So if I increase any of these guys here, it's going to increase my inductance. If I decrease any of the guys here, it's going to decrease my inductance. So proportional. Okay, increase or decrease any of these guys, it's going to do the exact same thing to my inductance. But the length of the flux path, okay, if I increase the length of my flux path, it's going to do the opposite. It's going to drop my inductance. Inductance is going to go down. If I decrease my flux path, my inductance is going to go up, right? And you can think of inductance right now as kind of a resistive portion of your circuit, in a sense, okay? So the whole purpose of this is getting to a contactor, right? When this coil is energized, these coils here are energized, and I have a magnetic field, right? The magnetic field has to travel through an air gap here, all right? And that air gap is represented by your flux path. So how far that flux has to travel through that path to get to the armature, to pull it in, right? So right now I have an air gap, and we know that lines of flux don't really like traveling through air, but they will. They'd much rather travel through something like a soft iron core, like this guy here. So right now, my armature's open. I have air gap here, so I'm starting to put some voltage through, okay, putting it through my coil. When I get to 85% of the voltage rating of that coil, my armature is going to pull in, and that flux path is going to decrease, right? So if I go back to this formula here, my flux path, this little L down here, right, if that decreases based on what it is and what it turns into, right, that's going to decrease, which means my inductance is going to go up, right? Okay, so right now, before we do anything, right, before armature seals in, we have a long flux path, so that's that air gap right there. We have a low inductance, so in henries. So my inductance is low, which means my current's high. We have a low inductive reactance, right, or XL, and we have a higher current. Okay, so after the armature seals in, right, that path for my flux to travel through, it shortens, so a very short flux path. We have a higher inductance, so in henries. So again, your inductance, or your flux path goes down. Inductance is going to increase, right? We have a higher XL, right? And we have a lower current. So what happens is, if I have a higher inductance, right, I'm going to have lower current. If I have lower inductance, I'm going to have a higher current. So right off the bat, when my armature is trying to pull in, until it gets to that 85%, my current is pretty high. It's really high to get those that magnetic line of flux to actually be able to travel through the air here into the armature until it hits 85%. Then it's going to pull it down. The armature seals in, right? Which means my flux path is now diminished and almost gone, which means my flux path is lowered, right? Which means my inductance is going to increase, and as my inductance increases, my current is going to decrease, which is a good thing, because these coils here don't like high current. I got high current in those coils, and that means they're going to burn out. Right? So if I get something jammed in here, right, if I stuck my finger in there or a piece of wood in there, and then turned on that circuit, this coil is going to be seeing a high current for a very long time until that piece of wood is removed or the coil burns out. Right? So we want that armature to close quickly to reduce that current, get it low enough that the armature is touching, and the coil is not going to burn out from that higher current. Right? It's always, always, always about current. Okay, so here we have a little graph for you. So we have coil current on the left-hand side here in amps, so 0.1 amp or 200 milliamps, 200 milliamps up. Then we have the voltage across the coil in volts, so 20 volts up to, say, about 120 volts here. All right. So as your, again, this goes back to the 85% seal-on and 50% dropout voltage. So as my voltage starts to increase going to that coil, right? So I'm at about 20 volts. My current is also rising, right? So my current's going up, my voltage is going up, right? Right when I get to about, where is it? The seal-in voltage, so about 85% here, right? I get to 85% and my voltage is, sorry, at 85%, but my current is going to drop, right? So once I get up to right about here, my current's going to drop all the way down, which is a good thing, right? It's going to drop all the way down here, and my voltage is still going to increase until 120 volts, okay? Now when that sine wave hits its peak and then starts coming back down, my voltage is dropping from 120 volts to 0 volts. And when it gets to that 50% rating, that means my armature is going to drop out. Okay? So, as I increase my voltage, my current increases, right? And then once my voltage gets up to a certain amount here, right? 85%, it's going to seal in that armature. Right when that seal-in of the armature happens, my flux path reduces. My flux path reduces, that means my inductance is going to go up. If my inductance goes up, that means my current, as we see here, is going to drop way down. And that's going to protect our coil. All right? Now, the next one, if we have a dropout voltage, so once my voltage drops down to about 50% of the rated voltage for that coil, right, the voltage is going to drop, obviously, right here, right? But then my current's going to increase, right? So 50%, but again, your voltage is at 50% now, so your current's not going to be super high. It's not like it's at its maximum value, 120 volts, based on that current, right? It's dropping down rapidly to 0 here. Once it hits 50%, armature is going to open up. Yes, you get that flux path is going to increase, but your current is already on its way down, so we don't really have to worry about that. Okay, effects of incorrect voltage, right? And they're talking about coils here. You can see that coil is a little bit charred right here. If the voltage is too high, right, your coil can burn out. We all know that, right? But also, if the voltage is too low, the coil can burn out. Why, do you ask? Well, going back to this guy here, actually, let's go back all the way here. If I have, say, a coil rate for 120 volts, right, I need at least 102 volts to get my armature to seal in, okay? If I put anything above 120 volts, say 130 volts, it might be okay. If I get much higher than that, I'm running a risk because my voltage is going up. It means my current's going up, and I'm going to burn out my coil. Okay. The problem with a low voltage is if my voltage is not strong enough to actually pull in this coil, pull in the armature, that means that my my flux path here is never going to decrease because my armature is not actually pulling in, right? So if this does not decrease, that means my inductance is going to be small. And if my inductance is small, that means my current's going to be high. So if I don't have enough voltage here to actually get that seal in voltage, to get that armature to move, that means my current's going to be really high on this coil for a long time, and I can actually burn it out. So too high a voltage is bad, and too low a voltage is also bad. All right, contactor classifications. All right, we have NEMA versus IEC. All right, so NEMA stands for National Electrical Manufacturers Association, and IEC stands for International Electrical Commissions. So NEMA is what we're going to be using in the labs, right, for the most part. So the National Electrical Manufacturers Association. These contactors here, these are the only two we're going to really be talking about. But the NEMA contactors are usually larger, used in North America, and they're really easy they're simple and really easy to use, and they're pretty much like a general use contactor. The ones with the NEMA symbols here, right? IEC, they're going to be smaller and lighter. They're European, right? And their emphasis is on design for specific applications. So these are a more general use. You can use them anywhere for anything, for the most part. These ones here, they have specific ones for specific uses. So they're not a general use application. So they can be a little bit more finicky. All right. So like I said, in North America, we're using these guys here. They're a little easier. They're a little bigger, but that's okay. They'll hold up. So just know your NEMA compared to IEC, what the two meanings are: National Electrical Manufacturers Association and International Electrical Commission. All right, we have types of contactors. We have a standard non-latching or non-reversing contactor, right? So here we have a breaker, just regular plain Jane. It's like probably it's 15 amp breaker. Cool. And that's feeding into a contactor, which again, contactor is just a large relay. And based on that contactor's position, it's going to turn on or off a light, okay, or a load, right? So going to, right, we have mechanical latching contactors. So we have, here's some contacts here. We have our armature, right? We have a latching coil and a magnet, right? And an unlatching coil. So we have a latching mechanism. This part right here is what latches it on or off. So a latching coil, you bump a current to the latching coil. It's going to pull the armature in. Okay, it's going to close the contacts, and this the latching mechanism is going to straighten out just like this, and it's going to hold the contacts in place, right? Until you bump the unlatching coil, right, which is going to move this armature, right? It's going to bump it out, move it down, open up these contacts, turning off your load. All right, so kind of like an ELV solenoid, how they latch in place, you can have mechanically latching contactors as well. So you don't have to have a constant current going to a coil. You just have to bump that coil to latch it on or to latch it off. Okay, and that means your coil, and usually these guys here are going to be cheaper because your coil is not going to have a constant current going through it or a constant voltage. So we don't have to worry about making those coils super heavy duty to handle a constant current to them. So you're just bumping a current on and bumping a current off. Right? So they also have mechanically interlocked and reversing contactors. So mechanically interlocked is how to explain this? You have a non-reversing contactor, so just a plain Jane contactor. Okay, you energize a coil, it's going to shut or open contacts. Done. Right? Then you have the same thing on this side. So just two of them. They're plain Jane non-reversing contactors. Then you can have a mechanical interlock go between the two, and they fit in. You can see the slots here. They fit in. Which, what it's going to do is, you can have this one running, right? This one turn on, but this is going to mechanically lock this one so it cannot turn on. So you can never, ever, ever have both of these running at the same time. So if I'm trying to run, and this is used for reversing and non-reversing motors, okay? If I have my motor on forward, okay, I don't want to be able to go and hit the reverse button and have the reverse and forward current going in two different directions, okay? That'd be not a good thing. So we have mechanical interlocks to not allow that to happen. So this one would have to be turned off first, and then it would release this one to be turned on or nothing. Okay. Definite purpose contactors are for HVAC, right? These guys here are mainly used just to operate heating and AC units, right? So these guys here are used provided they have an automatic thermostat somewhere in the building to operate them, or they can have manual operation from a thermostat inside the building. They're especially made for HVAC units. HVAC units, heating units, and AC units. Okay. All right, then we got motor control. So we got that breaker, right, controlling a contactor, which is going to be controlling a motor. All right. So we can't just have a plain Jane contactor, controlling a motor. We have to have a contactor going through overloads, which are then going to control your motor. It's contactor plus overloads equals a motor starter. So this is here a motor starter. These two things combined is a motor starter. So we have a contactor, which again is just a large relay. And then we have an overload block. The overloads are to protect the motor. If something happens and that motor is drawing too much current, the overloads are going to trip, not allowing that motor to burn out. Right? So we have our coil and the core. Right? These are shading coils, which I'll get to in a little bit. We have our armature here. Here we can have, we can see those. These are the contacts, and those are those springs to allow the contacts to hit and not to bounce. So it's going to reduce the amount of arcing. Okay, contactor springs right here. They absorb the shock and maintain good contact. It's a good little breakdown of what is inside of a contactor here. We have an armature spring or a return spring to help that armature return back to its original state as quickly as possible, again to avoid arcing. All right. Then we have the actual nameplates and ratings of your coils, right? Which is really important because we don't want to overload or underload our coil. As we know, it can start to burn it out. So here we have, so it's a poly three-phase, right? So horsepower maximum, so 200 or 230 volts, or 460, 475 volts, right? It says max AC is 20 amps, right? And then here's a coil, right? The coil is rated for 208 volts based on 60 hertz, right? So that's the maximum voltage you can apply to the coil before you start risking the chance of burning it out. All right. So here we have 120 volt, 60 hertz, or 110 volt, 50 hertz coil. So you got to look at those ratings and make sure that you're not going to overload or underload them. All right, here's your armature and your cores. All right, we have laminations. You guys remember back from first year, we talked about laminating a core. You can laminate a core in motors, in transformers, in armatures, and pretty much any core. The reason we do this is to reduce, now we can't get rid of them, but we can reduce the eddy currents that's happening in the core. Eddy currents are when a magnetic field is cutting through your core. It's the same thing as a conductor cutting through a magnetic field. It's going to induce a voltage and a current. So it's inducing a voltage and a current into your actual core here. And inducing a large current and a large voltage into this core, it's going to produce a lot of heat. So what they do is they take tiny little slices of your core and they isolate them from each other, and then they glue them all together. Right? what that's going to do is only allow a small amount of eddy currents, right? So your small amount of heat to build up in each one of these guys. So again, it doesn't get rid of the eddy currents. It just helps to reduce the amount of eddy currents, which is going to reduce your heat, which is going to make your transformer, your relay, whatever it is with the core, more efficient. Because again, that heat is power, and you're paying for that wasted power, right? So we want to try to reduce that as much as possible. Then we got shading coils. What the heck is a shading coil? Pretty much just a continuous loop of usually copper, right, around a pole in your relay, or your contactor, I should say. Okay. I think I have, I don't have it. Okay. What a shading coil is used for is when your armature, it all goes back to the seal-in voltage and the dropout voltage, right? When you have the seal-in voltage get hit by 85%, it's going to pull in your armature, right? And you have a magnetic field traveling in a certain direction in your armature, or in that core, all right? And what it's doing is that magnetic field is also cutting through the shading coil, right? And this shading coil is inducing a voltage in it now, just like those laminated pieces of the core here, right? And if I have a current and a magnetic field, it's going to produce a magnetic field also in the shading coil. And then when my voltage starts to drop on the sine wave and I hit 50%, I'm going to get that dropout voltage. So my armature is going to want to pull away, right? And if my armature pulls away, and then I'm going to get arcing. And if my armature pulls away, and then, I mean, this is happening 60 times a second, so it's very quickly. But my armature is going to pull away, and then in the next second, not literally in the next second, but it's going to jump back up to the seal-in voltage, and your armature is going to slam shut again. So what you can have happening is you get chatter. Your armature is opening and closing super quickly, right? So you can hear like a buzzing or a chattering noise coming from your contactor, which is not good. You don't want that. It's creating heat. It can damage the actual armature and the contacts because it's all vibrating and moving very quickly. So you have a shading coil here, and what that does is when that armature starts to drop out because the coil has hit its dropout voltage, armature is going to try to pull away, but this shading coil here is now emitting a magnetic field in the opposite direction, and it's actually attracting the other side of the core to the shading coil. So when one magnetic field drops out, the other one's going to increase, right? Because you have a magnetic field dropping, it's cutting through the shading coil, which is inducing a voltage in it, and now producing a magnetic field, which is then creating a magnet and keeping your armature locked in place. So it's going to reduce that chatter. Okay, so really, it's really a simple thing, right? But it's just shading coils are used for reducing the amount of chatter or movement of an armature as your seal-in and dropout voltage happens 60 times a second. Hopefully that makes a little bit of sense. If not, please ask me, and I'll try to re-explain it. All right, we have shading coil flux and out of phase with the supply flux. Okay, so we have our supply voltage here. This might explain a little bit better for you. Our supply voltage is increasing, right? Which is then based, so this is voltage here, and this is time. So as my supply voltage increases, right, I'm going to start to induce a voltage from the shading coil based on that magnetic field. So that shading coil is being cut through by magnetic field, and I'm starting to drop the voltage here, but the shading coil is just lagging behind it a little bit. So when this guy gets to 0, right, I'm still at a certain amount of voltage here, which is holding the armature. And by the time the shading coil magnetic field or the voltage drops to 0, here I have enough voltage being brought up here, and it's probably past that seal-in voltage, which is going to hold that armature in place until it goes around the other side. Okay, so when one magnetic field drops, the other one's still in play a little bit, just long enough for the other one to catch it and for it to maintain its seal in voltage. Okay, here we have a coil, our control contacts. So this is the contactor here. Control contacts, and we have our power contacts. Right? So control contacts would be like your control device that's inside or being used by your control, your contactor. So it can be hooked up to something indicating that the contactor is energized or de-energized. Okay, but your power contacts are what we worry about: line 1, line 2, line 3. So this would be a 3-phase, right? Your contactor has a set of contacts for each phase of that circuit. Okay, so relay standard contacts, just like the one we showed at the very beginning here. We have our electromagnetic field, or our core, and our coil. Right, we have our armature here with our contacts. So these are standard contacts here, which you would see in this ice cube relay. They're called one make and one break per pole. Right, so your armature has one portion of it, one piece, that's going to come in contact with either side of these contacts here. All right. Big contactors use bridge contacts. So bridge contacts are really good for alignment. It keeps the whole thing in line, as a wiping action, and produces arcing, because we have two places for the current to travel through. So it's going to reduce the amount of current going through that one point, right? So the amount of arcing is going to be reduced based on the amount of current going through that one point is going to be reduced. So here we have bridge contactor here, right? When it closes, obviously these two contacts are going to be in place here. So we have a current going through here and here. So it's split into two compared to going through only one spot. So the amount of currents can be reduced, which means the arcing will be reduced when this thing is opened up if there's a current traveling through it. Right? So we got our stationary contacts on either side here, and we have our movable contacts. And what happens is when these contacts actually open and close, it's called a wiping action. And the wiping action can actually help clean off debris, carbon, whatever's been built up on these contacts to make it a nice clean contact. So we're going to reduce heat, we're going to reduce arcing, etc. So bridge contacts are great for that. That's why they're at an angle here, is to give you that wiping action to help pretty much self-clean those contacts. Right? Okay, then we have bridge means double make and double break. Right? So that means that when this armature is pushed down, you have two makes. It's going to make on either one here, and when you open it up, it's a double break. It's going to break at 2 points here. And again, that's going to reduce the arcing that's going to be happening in those contacts. So here you see them, right? Bridge contacts. When an armature pulls in, it's going to come into contact with both sides here, and it's going to give that sweeping action that's going to actually self-clean those contacts. Okay, I think I'm going to stop here for today. We'll try to pick this up. That was a lot of information. We're going to start to pick it up from here on the next class. So please go through your ILM, read up on this, rewatch this video if you need. If you have any questions about any of it, please contact me and I can try to explain it in a different way or better. But yeah, that's a huge module to try to take in, and I'm already at about 50 minutes here for a lecture, so I think that's probably good enough for today. Anyway, please let me know if you have any questions. Hope you enjoyed, and I will chat with you next class. Take care.